very much, Yves, for the great introduction, and thanks much for having me here to speak. I really appreciate it. I see a lot of familiar faces here, so thanks for coming to see. I'm sure this is old hat for you, and I haven't given this talk before, so please excuse any typos, inaccuracies, and things like that. So I just wanted to echo Yves' sentiment about Python and finance. Actually, Mark Higgins and I started the Athena project at JP in 2006, and people told us we were crazy for using Python. And funnily enough, the reason we picked Python back then was because we're like, well, Python seems like a decent language. Let's do a few Google searches. And we looked at, I think, Ruby and Python. Python got more hits than Ruby. But it was a good choice, I think. So I was going to talk about dependency graphs in Python, and I'm sure being in finance, you guys have all used, I think, what's the most successful platform in finance, which is Excel. So we all love and hate it, right? And I really like Excel for prototyping and playing with stuff and things like that. And I think one of the cool things about Excel is that all your intermediate computations are exposed. It's very transparent. You can easily step down into something to see why you came up with a value. And so everyone pretty much tries to invent things like that in other languages. There's various caching, memoization frameworks and things like this. But they're all somewhat ad hoc, and Python has memoization decorators and things like that. So this is an attempt to have a slightly more formal way to do that. And I think it ends up being useful. So let's see. So we'll talk a little bit about. Let me stick my phone up here so that I don't. So I remember what time it is. And if I'm looking down, it's not because I'm texting anyone. So design principles. I think one thing which is important is we want a sort of a lazy computation framework, because we want to be able to express very, very large computations, be able to distribute them, be able to sort of execute them on demand and things like this. We don't want expressing a computation to actually have to instantiate the whole thing. And then, of course, we also want a memoization framework because, for example, if you've calibrated an expensive wall surface, you want to be able to use it with impunity without having to think about, is it dirty? Do I need to recalibrate it? Have I changed some inputs, etc.? So one of the ways we'll think about doing this is by doing parse time dependency analysis. So we will impose some restrictions on syntax, and we will use essentially a syntax tree transformer, which Python makes very easy to recognize certain constructs, transform them, rewrite the code, and execute it, still using the same Python VM, but just with a slightly different computation model. We could also look at ways to compile this down into assembly. There's lots of frameworks using LLVM and all now as well to do this. If you know types and you know the data flow, in theory, you should be able to make it much faster. The other thing that's really key about having sort of this memoization framework is that you want side effect free functions. If you call a function twice with the same inputs, it should give you exactly the same value. That's not surprising. Excel does that too. In a sense, formulas in Excel are just pure functions. You can't do very much with them. People resort to Visual Basic and things like this. So we want to do better than that, right? And of course, the values must be immutable. That's a bit of a challenge in Python. There's no const values, so you kind of have to trust people. But it's just a convention. There's various ways you could do, for example, to check that as well. You could copy values and then rerun it and check to see if the values have changed. So there's debug modes that you can write to make that happen. And a couple of other features which we'll talk about, depending on how much time we have, is we want a notification framework, because if you have, in Excel, the cool thing about Excel is that the model, the view, and all is the same thing, right? You see all the data there. You change something, immediately the user interface updates, essentially notifications. But we want to be able to do a little bit better than that. If you look at all these new HTML5 frameworks, AngularJS and things like this, also C#, WPF, they all support data binding. Notifications on a dependency graph is very useful to actually support an efficient way to do data binding. We can also do input discovery. So say you've built like for example in Excel, you have a graph of formulas. It would be very nice to know, is any of these things an input that I care about? For example, a spot of a currency pair, a yield curve or something like that, be able to tweak that, etc. And then we'll also have a notion of bindings. So since this is a pure immutable graph, we want to be able to bind values temporarily to change them to see how the effect of that would be. And we can also use this for parallelism, asynchronous execution, and things like that. So I talked a little bit about memoization earlier. And so we will add dependency tracking essentially by parsing references in the syntax tree. And then we'll expose each of those memoized function calls as nodes in a dependency graph. Again, just, Excel is a very easy way to think about these things. Every cell is a function essentially. And cells depend upon other cells. You can hit that little key in Excel, which my fingers remember, but not my brain, which shows you the arrows that go into a cell. And also laziness. When we bind values to change them to see their effect, we don't want to trigger computation. That would be very inefficient. This is not a data flow engine like a CEP engine. It's really just expressing computation. So bindings propagate invalidation, essentially dirty flags. They don't trigger evaluation. And in order to be able to express computations, we really have sort of a base state of a graph. Think of a spreadsheet. You can then change a bunch of cells. That's a set of bindings. And then you can execute that as a computation later, push it off to another node if you want to distribute the compute, et cetera. So we'll think about things as sort of sets of bind operations. And of course, since we have a real object-oriented language here, we can, we get the benefit of abstraction. We have classes. So for example, you can override certain functions and change behavior, et cetera. So very convenient. You can delegate implementations, et cetera. And we also have a notion of namespaces. Again, think about Excel, you have a named range, very useful, right? But we'll take that a little bit further and have these things bind to a database, essentially, or a file system, or whatever you like. We talked a little bit before about the notification framework. So, this also lets you, since you can separate your data flow from your views, you can sort of build a true MVVC architecture. So you have your views, which could be JavaScript web UIs, C# UIs or something with a back-end compute engine, which can notify you when things change. So it leads to very clean separation if you do it that way. And it's also efficient because unlike things like AngularJS and things like this, where you have data binding, the only way they know something is dirty is that they have to reevaluate the functions all the time, right? And so you have to build all these caching mechanisms in there. I've been playing with some of these things over the last few months, and I was like, damn it, I need a graph. I need to know when things are dirty. so this is, it's useful to build again. And then, of course, side effect free. So if you're side effect free, it's very easy to distribute a computation. All you have to do is express the set of changes as a set of bindings. You can then apply those, compute them wherever you like, distribute them, parallelize many cores, etc. So, having done this a couple of times, everyone looks at this and says, why do I need a framework? Why are you adding all these restrictions to Python? I can do this in many other ways. I can add memoizing decorators. I can just have a plain old cache. I call my function, and function says, ooh, I look at my inputs, look this up in a dictionary, give you back a value. I think the biggest problem with all these approaches is, well, everyone does them slightly differently, is that they're opaque. So your your dependencies are not tracked. So for example, if I have a memoizing function, I call that function, I've essentially sort of thunked it, I get back a value. I have no idea what went into this computation. I have no idea when this is dirty. I have no idea, how to debug that call. I just end up with a value at the end. And unlike Excel, for example, I can't step through it. I can't inspect it. So I think that's in my mind, that's one of the key reasons why you want a framework to do things like this. And I think the other reason also is that if you think about a computation, you're calling a function which calls another function. You essentially have a chain of function calls. What's very useful, I think, if you're trying to define scenarios or do some kind of financial computation, or in other applications that you're writing to, is you want to change something and then figure out what's the affected path, a chain of function calls that you would want to reevaluate. And that, again, is not possible unless you have some form of dependency tracking, or you can track the function, the chain of function calls. And most memoizing frameworks, just really don't let you do that. So you can't rebind and reevaluate an affected path. And of course, they also lack dirty notifications. So what we'll do is we'll introduce a notion of a side effect free function, which we'll call a Ceph, which is not a swap execution facility. So that's why the extra F, short enough to type. So it's in Python very simple. You just have a decorator, and what it does is it analyzes the syntax tree, infers inputs and edge inputs. We'll talk about this a bit later, and just rewrites the code. Does a syntax tree transform, regenerates the code, and it should just work. And in order to support, and so these are free functions. In order to support some notion of abstraction, we'll bind these to classes. And so essentially self becomes your free variable there, which you can use to get to other functions. You can also use it to get to a namespace, etc. In theory, you could have a more complex form of free variables with constraints and things like that, but it's kind of hard to know how to express that. So any ideas anyone has, I'd be very happy to hear. And objects are also implicitly bound to a namespace. I mean, if you think about it in Excel, every cell is implicitly bound to a namespace, is the name of the cell. Using Cephs, you actually bind the object itself to a namespace, which is a GUID if you don't specify it, or you can give it some well-named thing. Like, for example, I could say assets, currencies, USD. And then anyone who wants the USD object can go there, and they can ask it for a yield curve, and then you have some shared value. Very much like a named range in Excel, except it's an object, not just a cell. And so we'll take these Cephs and bind them to objects. So we'll call these graph object models, short for Gromit. Anyone who watches Wallace and Gromit. If you haven't, great claymation. I also like cheese, and there's a great, they go to the moon to find cheese. Anyway, I'm getting off topic, sorry. So it's a common base class, basically. It just adds namespaces and some graph integration. It basically hooks into every function call invocation, and whenever you call a function, instead of calling the function, it looks it up in its cache of nodes, maps it to a node. If it's valid, gives you back the value. Otherwise, goes and does the computation. There's no implication on plain old Python functions. So if you have a member function of a class which doesn't have this Ceph decorator, it behaves, just as usual. And since we talked a bit earlier about, side effect free functions and externalizing all the bindings, that has a bunch of implications. So what that means is that member variables don't work, because there's, we don't really want to instrument getAttr, and I think that would be a confusing syntax. It's better to have a variable be a no argument function call, very much like Scala, which has no argument function calls. But Scala goes a little bit further, I guess. It lets you access them as properties, which you could do the same. Oops, geez, oh. Too excited there. I think I drank too much coffee this morning. Yes, so you could do the same with Python too, right? Properties do gets and sets and things like that. But anyway, I like the function call syntax. So member variables are not tracked and discouraged. You can, of course, use them as plain old Python objects, right? But remember that they won't be externalized. The whole dependency tracking mechanism doesn't work. So you replace them essentially by functions returning constants. And in fact, the function doesn't have to return a constant. It could actually even compute a default value. So say I have an option. An option has a member variable called strike. Instead of a member variable, you would actually make it a function called strike that returns, say 1. That's kind of silly, right? Because you don't want to hard code the constant, since we have all this nice abstraction framework. Ideally, you wanted to say ask whatever asset this option is on, and return, say, the at the money forward. The forward curve on the spot date, which is your at the money strike. And then that's very convenient. It makes it very convenient to set up these little options, sort of regardless of what asset class you have. And if you go serialize this object, you can flag these things as serialized, and it will just freeze that value. So very convenient. So here's a very trivial example. It's always hard to put code up on the screen, but I thought this is easy to show, why, for example, Memo is, this framework, just how code rewriting works. So stupid little Fibonacci function returns 1 if n is less than 2. Otherwise, recurses n minus 1, n minus 2. If you run this just as a standard Python function, this is exponential, right? It's approximately 2 to the n. But if you think about how this is going to execute, if you have a caching framework, it becomes linear time, because the graph object model simply caches all invocations of the function, and it will just run in linear time. Of course, it uses a linear amount of memory as well. So how this decorator basically works is a little bit under the hood. It will rewrite that function into something that takes a node, which is what it's evaluating, and a list of input values. And so the code transformation looks kind of like that you've replaced every method reference, like self.Fibonacci of n-1, with simply an index into an input value array. And at the bottom, you see what the graph, what the Ceph parser infers about what the inputs are. Input number 0 is just the argument. 1 is Fibonacci of n-1, and we also have conditionals. So there are certain inputs that will not be evaluated. So if you think about setting up a dependency graph like this, if you evaluate the inputs before you enter the function, you would never stop, right? Because you would keep building the graph, or you go on to infinity. So you need somebody to essentially cut them off, kind of like a prolog cut or something like this. So you would basically say certain branches of this tree should not be explored if some conditional is met. So again, so this has some implications on computation order, as we just mentioned. Like, for example, if you look at this Fibonacci function, so inputs are pre-evaluated. So stepping through an invocation is actually bottom up. So when you call the function for n, the function for n doesn't get entered until the inputs into that function are evaluated first. So if you look at Fibonacci of 5, the order in which it will actually call the rewritten function is in this inverted order, 1, 2, so on, up to 5. Same result, these are side effect free functions, but it may be confusing in debuggers. We also get a couple of implications on exception handling. So again, if you don't actually call a function until its inputs are satisfied, if you throw an exception, you can't catch it. If you throw an exception in a function that you call, you can't catch it in your function because your function hasn't even been called yet. So really, basically what this means is that you still get an exception, and if you have plain old imperative Python, the exception will be propagated back to it. You just can't catch it within one of these pure functions. But this doesn't actually change the behavior because those pure functions aren't actually valid. So once that exception the cause of that exception is fixed and you reevaluate this, that chain of functions will become valid again. So every graph exception essentially carries its own traceback. You can still inspect where it came from, and then you can retry after you fixed the error. You can also do a couple of other things. For example, a Ceph could declare an intention to handle errors. It can say, okay, if I get an exception in something that I'm going to call, think about Excel. You have a chain of cells. One of these cells raises an error. Some cell depends upon it. You could say, I can handle errors. Just tell me I got an error. And then it computes a different value. And then essentially turns itself valid, and then keeps going up the chain. And there's a couple of implications there too, because if you think about invalidation and dirty bits, you don't want to repropagate them through paths that are already dirty. But in a case where you have something that's going to handle errors, you do, because the cause of the error might change. So you might want to reevaluate this path even if it's dirty, right? Because this guy up here is handling errors. You could actually keep track of what error it was and compare errors, but I think comparing values is always a little dodgy. So under the hood, basically what we do is we transform function invocations into nodes in a graph. We have two kinds of nodes, basically. One is terminals. A terminal is a constant. So a terminal has no inputs. It has simply a value. So it's going to be constant argument values. It's the object instance. And the key is implicitly just the value. So you hash it and look it up. Simple implication is just like a dictionary key. You want a stable hash and equality. If you don't, bad things will happen. The majority of the nodes are non-terminals. So those are actually like cells in Excel that are formulas. Think about this again as an Excel cell. A constant is a terminal. Anything with a formula is a non-terminal. These actually represent Ceph invocations. So the key is object, method, and argument, list of arguments. It's a tuple. So that uniquely identifies an invocation. The inputs to this are basically the values, which are other leaf invocation references. And then you have edges as well into these inputs. So if you have an intermediate reference, which we'll talk about in a bit, these change the shape of the graph. So this is something, for example, Excel does not have an analog for. So a leaf Ceph invocation is just like A1 equals A2 plus A3. So A2 and A3 are leaf references. But if you could actually compute what cell you're going to depend upon, that's an edge input. That's actually very useful. So these are the constructs basically that the parser understands. So it will take a syntax tree, and starting at known roots. So the known roots are going to be self, which is your instance variable, and any arguments. Essentially the terminal nodes that come into this invocation. Method invocations, very easy to detect in a syntax tree parser. You can do compositions. So I kind of think of this like Haskell monads. It has very similar notions. So you can compose invocations. You can do mappings, so which is a list comprehension. You can apply some function over another function. So you can say p.price for p in self.positions. You can't use a loop, right? Because think about a loop. If I'm going to loop and then call a Ceph function, the instance variable in the loop is imperative. So you can only know its value when you're calling the function. So you can't actually do it ahead of time. That's why you need to express things as a map. Again, looks very much like Haskell or Lisp or whatever it is. And conditionals. Again, we talked about cutting off branches of the graph. So you can say self.x if A, else B, which conditionalizes that branch of the graph. So you evaluate either X or B. I should have said Y, shouldn't I? Just to be consistent. And then, of course, namespace references. So this is like a named range in Excel. So I can go and look at the object which says, my name is env pricing. And you can bind this namespace to a database. You can bind it to whatever else you like. And then other thing is simple, pure expressions. So if I'm going to call an object, call a method with some arguments, that argument, again, has to be something that's pure, that's knowable. So that's either another Ceph invocation or an expression involving those. So, basically, internally, that would be translated into a lambda, which takes the value of n and returns, input values of 0, -1, or whatever. So, we can finally get to some demo silly finance code, since this is a conference for quants. This is a very dumb pricer. Sorry, it's hard to fit stuff on a page, but I just thought I would show some of the things that I was talking about. So if you just think about a European option, this is a stored value. That's the name of the pair, say euro dollar. And now you can think about expiration date, which is another sort of member variable of this thing. Instead of being a member variable, it's a function which goes to the pair, asks for expiry date rules, gets today's date, and then adjusts it by 3 months. So this is very convenient because I construct an object and I ask it for its expiration date, and implicitly, based on whatever pair or asset I have, it gives me a 3-month expiry. So it makes it very easy to set up things and play with them. And similarly, the strike is just going to the forward curve and getting the expiration date, so you have the money strike. So more interestingly, I can define a function called spot price, which computes some adjusted vol based on strike and expiry, some discount factors, and then calls option price. Now, once you've set this up, it's very easy so this is basically you can see a Ceph syntax is just pure Python. The implications really are that local variables can't be passed into other functions. They have to be just references of other Ceph invocations. Modulo all the syntax things that we looked at before. So once we've done this, we've really just built a fancy object-oriented version of Excel, because we've cached function invocations. We still have no way of doing scenarios and bindings and things like this. In Excel, you really can't do that. You could write Visual Basic, but Visual Basic can't really interact with a sheet. The cool thing about this is now we can actually interact with these objects using Python. So here's an imperative scenario. So I can say, price my option, do a bind, and I'm going to bind the spot to spot plus epsilon, And since I know all the dependencies, I'll just essentially dirty the path up to the price, ask for my price again. Oops. Oh, no, sorry. I thought I had the indentation up backwards. So within the binding set, I can ask for my price up, and that'll give me essentially my delta, right? Very efficient. It only recomputes a path that's changed, and I can, can script this, I can do whatever I like. I can define as many scenarios as I like, and you can see the object-oriented nature of it makes it very easy to know what your pair is, tweak the spot. Tweaking spot is actually an interesting operation because you don't really just want to rebind spot. You actually also want to change the forward curve. You also want to figure out which is your primary currency of your currency pair, do the right thing there, right? So you actually have a little hook to do that. Won't get to talk about it here, I think. It won't be enough time, and I'm not sure you're all interested. And of course, you can do other things as well. Since we have these namespaces, it's very convenient to do simulations and backtests. So in order to look up some piece of market data, say I have this pricing environment, which is an object, that tells me how to get data for today's date. I can just shift that and then look up data for another date. And so, with a bunch of conventions, it becomes very convenient to price things as of yesterday. So I can take the namespace of my portfolio here, rebind the dates to -1 business day, reprice. It will be my price as of yesterday if I've set up all my dependencies correctly. The other thing that this object-oriented abstractions make very easy is filtering for inputs. If I want to write a generic scenario, like in the previous case, what I was doing is I knew my object had a pair and I was going to tweak its spot. But say I have some complicated portfolio price and I know somewhere I depend upon currencies. I simply ask the graph to filter this portfolio price, just missing a comma there, I think maybe, going all the way down the graph and find me any node whose method is an FX currency pair spot. So this will actually build the graph but not evaluate everything in the graph and simply tell me anything that I depend upon that's a currency pair spot. And I can generically just say, I'm going to rebind each one of those dependencies to plus epsilon, recompute a price. And now I have a partial deltas for spot. So that's very convenient. And so depending on how you set up your conventions, you could do this for credit spreads too. You could say, for example, find me anything that has a dependency on a CDS. Bump CDS curves by 1 basis point or something and see what happens. If you have a hierarchy of credit issuers, you can say, find me all credit spreads that are Spain. And then bump those, and that's my Spain scenario, right? So it's very easy to express things like that if you set up your conventions right. Something that would be pretty much impossible to do in Excel. So what you saw there was basically imperative bindings. So you have function calls, you can change the state of the graph, you're changing it in place. That's a little restrictive, right? Because we already talked about Cephs being side effect free. So if I wanted to put something like a delta or a PNL as the result of a Ceph, I couldn't do that. Because as I'm doing that, I'm changing the state of the graph. I'm binding in place. So we'll introduce a notion of binding sets that we can bind to a node. So you can think about a node as being valid for a certain set of bindings. Everything that you saw before was sort of the root set of bindings. So that's the base binding set, so just one copy, right? The graph allows you to lift a new set of bindings. So for example, I can create like a little transparency. I can say on top of the space, you can think about it again as like Haskell, you have a monad that's a transformation from one world state to another. So you introduce a new binding and then and ask for a value. The graph engine will take care to copy only the subpaths that are changed, that it needs to lift into this binding space. And so let's see, just some syntax makes it a bit clearer. So say I'm trying to do a spot delta. I can define a spot delta binding which says, make a new binding set, B. I'll bind my spot, say this is a currency pair to spot plus epsilon, and I'll return that binding set. So now this is still a pure function. It took the current set of bindings, constructed a new binding on top of it, put a binding set, put a binding into that and returned it. So it hasn't mutated anything. And then if I want to do a delta, I simply say, here's my price, P0 price, flat, in the current binding set. Then I lift into this new binding set and I ask for another price. So that gives me my delta. So I can essentially take binding sets, put them on the graph, and construct sort of purely functional scenarios. So the reason we do all this is because we want to distribute computations. So if we really obsess about having things be completely not side effect free, being side effect free, etc., it's very easy to parallelize. You can simply take your binding set and your base state, send it off to somewhere else, recompute the value, and get it back, and it's going to be the same value that you had computed, if you followed all the rules, of course. And you can also take advantage of multi-core. So if your underlying Python libraries release the GIL, as the graph engine is going and evaluating functions, it can simply schedule them out to different cores. It won't help you much if it's all pure Python, because you'll just be fighting for the GIL. But if you're calling into NumPy or Skippy, it's sorry? Oh, that's right. I always call it Skippy for some reason. Yeah. Or if of course your underlying libraries don't release the GIL, you can simply take your input values, serialize them, and schedule that onto grid, get a computation back, and you guaranteed it's going to be the same, right? Because side effect free, supposedly. And pickleable, I forgot, right? You have to be able to pickle things, be able to pickle them efficiently, and things like that. So now most functions are pretty trivial, right? You saw here. So it's not very useful to go distribute every function onto a grid. Maybe multi-core would help. So we also introduce a notion of a do parallel. So you don't want to take every function and schedule it off on a grid. You want to mark certain functions as being expensive enough that you want to do that. So it's just a little hint. So we can tag it. Yes, I have a few more minutes. So I guess maybe I overestimated how much stuff I have. I got bored writing slides. So I think I'm a little early. But this is the stuff that I was planning not to get to, but I can if I have more time. So a couple of interesting things. So a side effect function can also return a future. So this will basically delay computation of all dependent values. Like assume I'm doing I/O, right? So I'm doing this big computation. I hit something. I want to do some I/O. Not very useful to stop, because there's a whole bunch of other things that I could do. So I can essentially return a future, and what the graph engine will do is it'll say, everything that depends on this value can't be computed yet. I'll go compute other things. So it just increases parallelism. So that's a useful feature. It's also very useful for like scheduling multiple I/O operations. So you can pipeline reads and things like this, get back up to the top, reapply all the reads, all the I/O requests that were satisfied, go on, right? So you get much lower latency. Notifications. So again, you can subscribe to be notified when the value of an invocation changes. As I mentioned earlier, that makes data binding very easy. So we talked a little bit earlier about all these functions being trivial, most of them being trivial in the sense that they're not useful to distribute. If you're going to cache every method invocation, you end up with a lot of memory as well, right? Because depending on how efficiently you implement a node, it's probably going to be about 30 odd bytes. It has inputs to all other nodes that it depends upon, so that's going to be 8 bytes for an input, 8 bytes back for an output, 16 bytes, 64-bit machine. I guess it doesn't matter so much if you're on a 64-bit machine, but it used to matter a lot more. So there's certainly some cost to it, right? So you might want to, and if you think about most computations that you do, you have an output, you have a whole bunch of intermediate computations, and you have some inputs here. All these intermediate values here are always dirty if you change an input. So you might want to collapse those, essentially reduce that graph into one supernode, which you can then execute using a little stack-based evaluator, send it off to a grid as a more expensive chunk and things like that. So you can define operators to do that as well. The other thing that's kind of interesting to talk about is garbage collection. So if you think about how the underlying graph mechanism works, is it caches a node based on the invocation of a function object, method, and some arguments. So even if I drop all references to my object, this cache is still holding on to this tuple that's holding on to this object, so my object never goes away. So that's a little annoying. So how am I going to collect this cache? I could do some LRU mechanism. I could randomly throw shit out and see what happens. And that's not wrong because it'll just be able to recompute it, but it's not also the most efficient thing to do. So what you really want is you want a completely weak cache, but that doesn't work either because it's the garbage collector will collect it whenever it wants, and then that's not useful because you don't get the benefit of memoization. So Python has a little hook, TP traverse. Anyone who's written C extensions is probably familiar with it. It's easy to abuse. So what you can do is you can simply take your nodes in your cache and say, these nodes aren't garbage collectible objects, so I'm going to hide them from the garbage collector. And I'll take each of my grommet objects, and when you call TP traverse on this object, instead it finds nodes on that which are invocations on that object and exposes their values as things that are reachable from this object. And that actually works remarkably well because it essentially, so if I have an object that doesn't reference any other objects as invocations, then that's fine. When I drop a reference to that object, I can now collect all the nodes that are caching values in that object. If I have a bunch of objects that mutually refer to each other, again, that works. It basically is a cycle in an invocation, which works just like ordinary cycles. And it'll collect both the objects and the nodes. And there's a couple of other little details, but I guess I'll leave some time for questions. I think that's pretty much all I had. I'll just go back to the front anyway.
This is probably an easy one for you. When you Google Ceph, do you get nothing but self references? So there's references to Python self, but not Ceph. Is that what's the distinction?
Do Cephs? Oh, that's just a name I made up, actually.
Oh. But there is, a general class of functions called self. So is it related to what you Google? You get back to Google?
To be honest, I haven't Googled it, so I should. I probably should.
Besides dependency graph, are you taking advantage of any big data platform or besides Excel? Because Excel has a limitation on how much data you can pull into, and also how's the performance. Do you have any performance issue when you trying to access data from Excel?
So,
Could you repeat the question?
yeah, so the question, I guess, is Excel has limitations on big data and on the size of the data set that you can store in Excel, and was the limitations on performance on accessing data. So this isn't really a data access layer. It's really just a computation model on how you would call functions. So it's the same problems. We don't actually use Excel for these things. Excel is just maybe a user interface to consume some objects that we would write here. But yeah, it's actually, I guess, I honestly don't use Excel that much. I'm probably not the best person to answer that.
Will you ever open source something like this?
Yeah, actually, so Mark and I are just co-founding a company, Washington Square Technologies, which is building this, and I don't know, we haven't decided. Yeah, go ahead.
In your call to the grommet filter method, I noticed that it didn't pass in a portfolio. So does the grommet object itself have the portfolio in it, or where does the ambient portfolio come from?
So actually, maybe I had a typo there, but the first argument to that was p.price, which is a method reference. So the idea is that's a delayed call. Sorry, there should be a comma here. So sorry, yes, P is a portfolio.
Okay, I see. That's
Right.
what I didn't.
Yeah.
Yes, thank you.
Right. Yeah.
I didn't see the definition.
Yeah, and so actually it's interesting. So if you call the function p.price, that would pass the value into it, which would fail. But if you just p.price, that's a delayed call. And so then it can essentially build a graph out of it. So the cool thing about defining objects like this and method references binding to nodes is that it's very easy to have a reference to a cell, not actually its value. It's really just the method reference plus some arguments if you have any. Okay, well, I guess thanks very much.